Silence, silence, silence. Oh, just kidding. Welcome, thanks for coming. Um, we, um, we got the survey results. We had an amazing response rate of 87 respondents, which is great, so good job you. The response to the survey was generally very positive, so we have decided to keep hosting these Science on Tap talks and social hours. So today we have wcoon, who will talk about sleep, memory, and schizophrenia.
John? Hello, my name's Will Coon. I'm a postdoc in Dara Minogue's lab up on the second floor. And I will give the same promise everybody does. I'll try to keep this as brief as possible, I promise. Today I just wanted to talk a little bit about some of the work that we're doing looking at sleep and its role in actively participating in memory consolidation, how this relates to cognitive deficits, specifically memory deficits, and psychiatric populations including autism, and today especially schizophrenia. This is a disorder that has a lifetime prevalence of close to 1%. Even after you successfully treat a lot of the more common positive symptoms like hallucinations, 20% of these people have difficulty working or holding down a job, and there's an estimated economic burden of close to $156 billion in 2013 alone. So there's quite an urgent need for treatments that specifically look at the cognitive and memory deficits in this population. And that's an ongoing kind of thrust of our research program up in floor 2 here. Since we're at an imaging center and this is kind of an imaging talk series, I wanted to talk a little bit about a unique imaging tool that doesn't get a lot of play. I think it's a little underutilized, but it's also difficult to acquire and get access to, and that's probably the big reason why. And it's something that I use in my research, and I'll just kind of illustrate how I'm using it to inform some of the research that we have in multiple ongoing projects upstairs. This is my PSA slide. If there's one thing you take from this and you can tune out afterwards, I won't forgive you. I will forgive you, I'm sorry. Sleep is really good for your brain and really good for memory. So if you learn something and you let some time elapse, if in that intervening period you've given yourself a good night's sleep, you will remember much more the next morning. So for those of you who tend to cram full all-nighters, this is my warning that that's not potentially the best route to do it. We've all done it anyway, I know. One of the more popular and widely replicated probes that we use to look at this phenomenon is a procedural learning task, motor sequence task. And this is one where we just ask subjects to learn an unfamiliar sequence and to repeat it as quickly and accurately as possible over several trials. And people are pretty good at learning this very fast. You can see there's kind of a steep learning curve here. Very quickly they reach a level of performance near asymptote, beyond which further training isn't going to yield any returns in terms of performance. We can let some time elapse and see what their performance looks like after 12 hours of, say, wakefulness, and we see no real evidence of improvement, but really dramatic improvements if we give them an opportunity to sleep in that same 12-hour period. And I think the debate about whether this is passive interference or active is pretty much over. The brain is doing a lot of things for you while you're peacefully sleeping that away, which is pretty cool. So just to establish a baseline, here's what the learning might look like in a series of controls, healthy subjects. They learn rather quickly here. They reach asymptote. And that's the bump we see in their performance if you test them after sleep. And now we can look to some of our patient populations. Again, this is schizophrenia specifically. And we find that they learn the task very, very similarly. The learning curve is essentially identical here. But they fail to seem to reap the benefits of the night's sleep. So something about their sleep is different that isn't giving them this kind of normal improvement that we see in typical healthy controls. And if we look at their sleep in kind of a macro sense, there aren't any obvious real differences. Their sleep on the whole doesn't look very much different from yours or mine. So we actually have to zoom in a little bit and look at some of the more subtle aspects of the brain physiology that unfolds across the course of a night of sleep and can tell us about what might be different in these brains versus the standard typical development case. What we find is a very pronounced reduction in the production of a sleep oscillation called the sleep spindle. These are brief bursts of oscillatory activity that are characteristic of the lighter stages of sleep, stage 2 if you're among the cognoscenti in the sleep research world. We find there's a dramatic reduction in the production of sleep spindles in these populations, and that the extent of this deficit correlates with their memory deficit as well. So there's evidence to believe that this is playing a causal role. You might think, since there are drugs available to us, common sleep drugs like Lunesta, which is a zopiclone. This is the Lunesta butterfly that some of you may recognize from the commercial on TV. Other drugs like Zolpidem, I'm blanking on the brand name for that one, but we can very effectively increase the number of spindles that a brain produces. But when we do it with, in particular, a drug like a zopiclone, despite the increase in the number of spindles, we don't see a concomitant increase in the memory performance that would be normally bestowed by sleep. So something about the spindles that they're producing isn't quite right in terms of trying to develop a treatment that can address these memory deficits. So this is a question I'm looking at, and it's not only trying to figure out what might not be working in this case, but it's so we can kind of increase our understanding of the physiology and try to develop more targeted treatments or identify other drugs that might increase the right spindle, so to speak. And in thinking about that, we have to remember that spindles don't actually occur in isolation. They unfold across a very specific electrophysiological backdrop that represents an incredibly complicated, orchestrated interplay around different brain regions. And when it's functioning normally, this is a way for the brain to synchronize activity across different structures that have specialized roles in the acquisition, processing, and distribution of memories, so that when they're functioning correctly, acting in concert, you have kind of a tripartite interplay where memory circuits that were engaged during learning episodes prior to a bout of sleep can be processed, packaged, and parsed by the brain from temporary storage in the hippocampus, and then kind of packaged, shuttled out to distributed representations and long-term stores and neocortical destinations where you can integrate it with prior experience. That's the system when it's working well. And the real emphasis here is on coupling. Synchrony is incredibly important, and the right temporal and spatial dynamics of these waveforms as they unfold across the course of the night is critical for their memory function. This is just kind of an idealized replay. I forgot there was an animation here, but this is a real-time kind of unfolding of what this might look like in an idealized case in your brain. I also think it's actually kind of profound to think that these little thalamocortical spindles wiggles you see, these are associated with hippocampal ripples down here, which are in turn associated with the reactivation of memories. So in a sense, you're actually watching a memory unfold in real time if you have the privilege of watching these traces go by on the screen. Again, coupling is key. And what we think is happening with the zopiclone in particular is it's increasing the wrong kind of spindle, the non-coupled spindle. So we see a spindle, we don't necessarily see a hippocampal activity in association with it, and we think this might explain why they're not actually performing the memory function they would in other circumstances. There's also some evidence in the animal literature that zopiclone, in kind of a double whammy, is also suppressing the hippocampus, so that's not so good from a lot of respects. Corollary of this is, of course, we think that effective interventions are going to be needing to increase spindles, but also attend to their simultaneous expression and coordination with these other important oscillations that we see in a normal, healthy brain. How do we test this? Well, we have access to sleep spindles. These are seen in the sleep EEG. This is non-invasive, it's inexpensive, it's widely available. But in order to look at the hippocampal ripples and to discern whether or not they're coupled with the things they should be coupled with, we need invasive recordings, at least in humans. And so this is a technique this is what I did my dissertation work on. It's an incredibly cool thing, electrocorticography. It's typically patients who have intractable epilepsy. It's resistant to medication, and they become surgical candidates for a resective procedure where a surgeon will try to identify the locus of an epileptogenic focus and then excise the tissue. They'll simultaneously be interested in mapping out areas of the brain we call eloquent cortex, which is not surprisingly associated with things like language, but also motor and sensory features. Areas that you want to preserve so that you don't impair function after the procedure. And most important to this story, it gives us direct access to things like the hippocampus. So in some of these very, very unique data sets, we have access to external scalp EEG that gives us information about these sleep spindles that we know are important for memory during sleep. And we can also tap into what's happening in the hippocampus. And we can compare them and try to understand what's different about what happens when they occur together and when they occur differently. So the idea might look something like this, and this is something that I'm actually starting to pursue actively right now. and I'll be looking at in much more detail in the fall. The idea is simply we have access to these two signals now. We can look at the hippocampus, we can look at the scalp, and we can feed these into something like an artificial intelligence. I'm not the biggest fan of that term, but everybody loves it. Really, it's a neural network, and we can train this network to look at these two signals and learn to discern between spindles that are coupled with the hippocampus and those that are different based on morphological features or other things that might be notoriously hard to tease apart from neural networks, other than the fact that we know they're very good at doing it. Right? The idea being here that once it's trained, we can jettison the requirement for these expensive and invasive techniques for invasive recordings and move simply to inexpensive, easily deployable EEG again. Now we have a classifier that's learned what to do with these signals, and it's very inexpensive then and very computationally inexpensive as well to apply it to simply scalp EEG signals and ask it simply which spindles does it see that are associated with the hippocampus and which are not. And this gives us an incredibly powerful tool. We can use this to look at the efficacy of potential novel treatments, different drugs that might increase coupled spindles, not just spindles without attending to the hippocampus. We can use that hopefully to kind of guide where we move next. Excuse me. Before we get involved in expensive clinical trials, right? So this is a nice research approach here. And at the same time, it's helping us better understand the physiology, what makes spindles couple, what makes them not, and what might we think about when we're trying to develop interventions that can be pharmaceutical and also electroceutical, since neurofeedback is getting kind of a resurgent popularity these days. And that's some work that some postdocs in our lab are also doing. Brian Baxter, I don't see him in the audience, but I'm sure he'd be happy to tell you more about it. And I just think this is a really nice example of something that I see a lot of times at the Martinos Center and that I never cease to underappreciate, I guess, or overappreciate rather. It's amazing how many different disciplines this draws on and how unique it is to be able to pull from clinical research expertise, from engineers, from applied mathematicians, from neuroscientists, behavioral and computational. I can't even list all the disciplines that go into this, but here you see this really unique opportunity to pull from all of these different backgrounds and generate some really interesting ways to look at questions in new, interesting, and I think very useful ways. So with that, and without any further ado, I will stand no longer between your snacks and your libations, as they say in my house at home, Nostrovia.
All right, thank you so much, Dr. Coon. So Dr. Coon will remain here for the next half an hour. So if you